Today I'd like to speak on the concept of prestressing structures. I hope to explain the concept and why it is used. I hope to describe some alternate methods used to prestress structures, briefly mention interesting historical examples, and finally discuss problems that structural engineers must resolve when designing and erecting prestressed structures. I'll be using some terms in an engineering sense. Therefore, I'll begin by explaining or defining some of these terms. Most fundamental is the concept of force. As defined by Newton, a force is the causative action for a change in momentum of a body or an acceleration of a mass. For example, the weight of an object is a force. Typical units to denote the magnitude or size of a force are pounds or newtons. I will be using the term axial force. If a member is long relative to its cross-section, a force applied along its length or in the axial direction is called an axial force, which may be either compressive or tensile. A second fundamental concept is that of force equilibrium. By Newton's law, if an object is not accelerating, the sum of the forces acting on it must be zero. The object is said to be in static equilibrium. The strength of a material generally depends on the intensity of an applied force or the force per unit area. Stress is a force divided by the area over which it acts. Typical units are pounds per square inch or PSI or newtons per meter squared or pascals. Stiffness is an increment of force divided by the corresponding increment in displacement. Typical units are pounds per inch or newtons per meter. For example, if I apply an axial force of 5 pounds to this rubber band and it stretches 2 inches, then the stiffness of the rubber band is 5 divided by 2 or 2.5 pounds per inch. Frequency is the rate of vibration, typically given in cycles per second or hertz. For example, the musical note middle C corresponds to a frequency of 262 hertz. Prestressing can generally be described then as follows. Prestressing means deliberately inducing a self-equilibrated state of stress in an object before it is placed in service. There are many possible reasons for wanting to prestress a structure. For one, prestressing may be essential for functionality. Prestressing can improve performance by increasing stiffness, frequency, or controlling cracking. Prestressing can simplify connections. Prestressing can preclude force reversals in members and allow use of tension-only cable members or compression-only contact members. Prestressing can decrease material usage and improve the efficiency of a system. Many common objects are prestressed. The blade in a traditional box saw is pretensioned to increase its out-of-plane stiffness. The prestressing is generally done by twisting a rope. The net of a tennis racket is prestressed in 2 directions to increase its stiffness when hitting a ball. For that matter, the surface of a tennis ball is prestressed in tension by its interior air pressure. Strings in musical instruments are also pretensioned to have the desired frequency or pitch. Similarly, drum membranes are prestressed to have the desired pitch. Tents are prestressed so they can form a space. Prestressing is essential for the functionality of tents. And of course, common barrels with wood staves are prestressed by circular steel hoops to seal them against leaks. In general, prestressing may be achieved by several methods, including pneumatically. Common examples include inflated balls, automotive tires, balloons, children's inflated play structures, inflated structures with an airlock for covering playing fields, pools, and so forth, or inflated pillows and tubular structures, as shown in this example in Osaka, Japan. Prestressing can also be achieved thermally. Tempered glass is processed such that the surfaces of a sheet are prestressed in compression while the interior is prestressed in tension. This greatly increases glass strength because the surface compression decreases the sensitivity of the strength to surface scratches. Wooden wagon wheels are a classic example of pre-stressing thermally. Wrought iron or steel hoops or tires were heated and then fit onto the rim of a wheel. Upon cooling, the iron contracted and pre-stressed both the rim and the spokes in compression. When a fully loaded wooden wheel rolled, all spokes remained in compression, including the one directly above the hub. Incidentally, the photo shows the famous 20 mule team wagons that transported borax from Death Valley 165 miles to the town of Mojave. The rear wheels are 7 feet in diameter. A third example of pre-stressing thermally are U.S. Civil War era cannons. Thomas Jefferson Rodman patented a process for making cast iron cannons that forced the inner surface of the bore to solidify first. As the solidification spread radially outward, the inner surface was pre-stressed in compression. The pre-compression on the inner surface of the bore greatly increased the life and reliability of cannons. An unusual method of pre-stressing is by using buckled elastic struts. The axial force that buckles an elastic strut increases slightly with increasing axial deformation. As highlighted on the slide, buckled struts were used for a design of a mast to support solar arrays on the International Space Station. The strain energy in the buckled struts was used to deploy the mast from its canister, and the forces from the buckled struts pre-stressed the mast and imparted stiffness. Sometimes adding weight can provide beneficial pre-stress. For example, if a concentrated vertical force is applied on a masonry arch, an arch can fail by forming 4 hinges and becoming a mechanism as shown on the drawing. If a weight is added in the spandrel area, as shown on the lower right photo, the force needed to perform a mechanism actually increases. As another example, tall wooden spires may be stabilized against overturning by wind by adding a weighted pendant. But the most common current way of pre-stressing large structures is by direct tensioning using hydraulic jacks and high-strength tendons. This slide shows a typical post-tensioning setup, in this case for a wooden truss. High-strength tendons are anchored on one end and at the other end are inserted within hydraulic through jacks. There are 2 sets of lock nuts and bearing plates, one above the hydraulic cylinder and one below under a so-called bridge. The bar is tensioned by extending the jack piston. At the desired bar tension, the lower lock nut is tightened and then the hydraulic pressure is released. Prior to hydraulic cylinders, pre-stressing was done by twisting ropes, inserting wedges, and later tightening nuts or turnbuckles. Examples reveal that pre-stressing was practiced throughout history in conjunction with most construction materials. Classic examples are Egyptian barges. The drawing shows that the barges had structures, now called hogging trusses, to maintain a desired curvature in the hull. As shown in the top drawing, the ropes were pre-stressed by twisting them. Another technique for pre-stressing used wedges. This is a partial elevation of St. Peter's Dome in Rome, which shows that it's girdled by 7 wrought iron chains pre-stressed by wedges to control or minimize meridional cracking. The photo at the upper right shows an actual chain joint, visible from the stairs used to ascend to the lantern. The coefficient of thermal expansion of iron is greater than that of masonry. Therefore, documents directed that pre-stressing should be done in warm weather, thus assuring larger pre-stressing forces in cold temperatures. 19th century U.S. truss bridges commonly used pre-stressing. 3 in particular were very significant. The patented trusses of Stephen Harriman Long, Williams Howe patent truss, and Thomas and Caleb Pratt's patented truss. Long's 1830 patented truss was all wood. He pre-stressed the truss by driving wedges at the ends of the diagonals as indicated in the highlighted oval. He thus caused compressive prestress forces, shown in red, in both diagonals, and tensile forces, shown in blue, in the verticals. The prestressing provided two distinct advantages. Long did not need to design any tension connections for the diagonals, and both diagonals contributed to the stiffness of the bridge. In his U.S. patent number 1397, received in 1839, he prestressed the truss by driving wedges at the tops of the verticals, as indicated in the red oval. He thus achieved a prestress state opposite to that of his 1830 patent truss. The diagonals were prestressed in tension, as highlighted in blue, and the verticals were prestressed in compression, as highlighted in red. However, Long had to design effective tension connections for both diagonals, a relatively difficult task for wood. Long's 1830 patent was made obsolete by the 1840 patent of William Howe, who introduced threaded wrought iron verticals and prestressed the truss by tightening the nuts. After a large-scale Howe bridge was completed over the Connecticut River in July of 1841, the Howe truss became the dominant form for U.S. railroad bridges. In 1846, Howe received U.S. patent number 4726 for nodal castings with sleeves that eliminated stresses perpendicular to the grain of the wood cords and thus markedly reduced prestress losses from time-dependent deformations in the wood cords. This is an example of a post-tension Howe truss. The high-strength vertical steel bars are in tension. The wood diagonals are in compression without positive connections to the iron nodal castings. That is, the diagonals are contact members that can only act in compression. In 1844, Thomas and Caleb Pratt received a U.S. bridge patent that made Long's 1839 patented truss obsolete. The Pratts introduced threaded wrought iron diagonals and prestressed their truss by tightening the nuts on the diagonals. Therefore, the diagonals were in tension, indicated in blue, and the verticals were in compression, indicated in red. This was the same prestress state as that in Long's truss of U.S. patent number 1397. By the late 19th century, the Pratt bridge truss was adopted by pioneers in flight. Octave Chanute and Augustus Herring built experimental gliders in 1896 and 1897 that were three-dimensional prestressed Pratt trusses. And Wilbur and Orville Wright also adopted the Pratt truss for their flyers. It is beneficial to pretension the diagonals because the vertical stiffness of the wings is increased when both diagonals are active. Having both diagonals tensioned also avoids the nonlinearities that occur when some wires go slack, and hence the predictability and the controllability of the machine are improved. Pretension diagonals have a greater stiffness and a higher natural frequency, and very likely less vibration from airflow. The objective is to prestress sufficiently to preclude slack wires under all predicted loads. Pretensioning was commonly done by inline turnbuckles. These are various biplanes in various museums. All have inline turnbuckles for prestressing. However, the two most well-known reconstructions of the Wright flyers, the one at the Smithsonian Institution in Washington, D.C., and the one at Carolyn Park in Dayton, Ohio, Wright's hometown, do not have inline turnbuckles. The reconstruction of the flyer in Dayton was begun actually under the supervision of Orville Wright and completed by Louis Christman in 1949. The next photo, taken during the reconstruction, clearly shows inline turnbuckles highlighted by red rectangles. A non-prestressed biplane will not function predictably. It is not possible to build a prestressed biplane without using adjustable length diagonals. The Wrights used adjustable length diagonals to establish geometry and pretension levels during construction. They then measured the exact lengths required and pre-made wires with soldered end loops. They installed the pre-assembled fixed-length diagonals by slipping the loops over hooks on the wings, and finally removed the adjustable wire diagonals. Prestressing is a difficult, time-consuming, iterative process. The Wrights had to disassemble and transport their planes from Dayton, Ohio to Kitty Hawk, North Carolina for flight testing. To facilitate the reassembly with the correct pretension, they substituted the fixed-length diagonals. Prestressing often permits replacement of most compressive members in a structure with very efficient, high-strength tensile members. An outstanding example is the cable truss suspension bridge at San Marcos, El Salvador, designed, fabricated, and erected by the John A. Roebling Sons Company of Trenton, New Jersey, under the leadership of their chief bridge engineer, Charles C. Sunderland. It was completed in October 1952. The bridge was pre-stressed by stretching the bottom cord, which was a bundle of 8 Roebling bridge strands. Because of the pre-stressing, it was possible to use high-strength cables for all the diagonal members. Ingeniously, the lower cord was anchored into the deck. Thus, its tension was equilibrated by compression in the concrete deck. But structural engineers often associate pre-stressing primarily with concrete. Pre-stressed concrete technology developed in the 1920s and 1930s largely in Europe, largely by European engineers. A principal objective was to minimize tensile stresses in concrete and hence minimize cracking, which then led to greater stiffnesses. 2 basic processes were developed. One is called pre-stressing. The steps are to first stretch tendons between bulkheads, then cast and cure a concrete member. The tendon and concrete bond as the concrete cures. After sufficient curing, the tendon is cut. As it tries to contract, it pre-stresses the concrete. The second is called post-tensioning. The first step is to cast and cure a concrete member with a duct. Then a tendon is threaded, stretched, and anchored against the concrete member, which pre-stresses the concrete in compression. In the United States, J.M. Crum and the Preload Corporation built pre-stressed concrete tanks beginning in 1931. The John A. Roebling Sons Company began research on post-tension concrete in 1944. They built and tested a 1/10 scale model of a 200-foot-long post-tension concrete bridge consisting of 5 segments. Pre-stress losses and displacements were measured for a 3-year period. Their principal observations were that time-dependent deformations of concrete caused some pre-stress losses and increased displacements, but that a permanent pre-stress state could be achieved, and that increases in displacements after the first year were negligible. The Roebling Company, under the engineering leadership of Charles Sunderland, also carried out a unique experiment with post-tension concrete. As a proof of concept, Roebling built a section of their Cicero, Illinois warehouse floor as shown on the drawing on the left. An unreinforced slab 9 inches thick was cast on sand. A layer of paraffin wax was applied, and then a 3-inch thick top slab was poured and cured. In October 1946, the top slab was post-tensioned in 2 directions, inducing a compressive stress of about 700 pounds per square inch in the concrete. The concept was that the pre-stressed slab would float over the base slab and remain uncracked. The former Roebling warehouse is currently a self-storage facility. In 2007, the parts of the floor that were visible were crack-free. The floor is without doubt the oldest pre-stressed floor system in the United States. The Roebling Company applied their post-tensioning technology on several of the bridges that they designed, fabricated, and erected. One was the Rio Paz suspension bridge between Guatemala and El Salvador, completed in 1949. The floor of the bridge was precast in 21-inch by 21 feet 7-inch modules. The modules were then post-tensioned along their lengths and then post-tensioned together longitudinally. The Rio Paz bridge is extant, but I am uncertain whether the deck is still the original one. Roebling concrete post-tensioning technology and products inspired other bridge engineers. Ross Bryan in Tennessee and C.L. Johnson in Michigan built block bridges in 1950 using Roebling post-tensioning products. These small block bridges augured the birth of an important new bridge building technology called precast post-tensioned segmental construction. On the left is an image of the engineer Gene Mueller when he was employed by the New York office of the Prestressing Company. He designed two small pre-stressed bridges for Wyoming County in New York State. On the right is the Griffith Road crossing of East Coy Creek. The bridge was built in 1953 by match casting 4 segments of a beam and then post-tensioning them together. Post-tensioning segments together may be demonstrated by a simple toy. It is made of beads or segments that are threaded together. The thread is tensioned by a spring in the base. If the thread tension is released, the toy collapses. If the thread tension is reapplied, the toy becomes stiff. This concept has been used to design truly remarkable, very large-scale structures. On the left is an image of the Confederation Bridge, which spans the 13-kilometer wide Northumberland Strait between the Canadian provinces of New Brunswick and Prince Edward Island. It was designed by J. Mueller International and completed in 1997 using precast post-tension segmental concrete construction. The image on the right shows the individual segments that were precast to form one of 43 main spans. The main girder is 192.5 meters or 630 feet long, and the drop-in segment has a span of 60 meters or 197 feet. The largest segments weighed 7,500 metric tons. A sense of the scale is provided by one of the smaller segments that is displayed in a bridgeside park on Prince Edward Island. The segments were post-tensioned together using very high-strength steel tendons. The image on the right shows the ducts for the tendons. A better understanding and appreciation of pre-stressed structures may be gained by briefly considering the engineering issues that arise during engineering design. One of the most important steps is to create a mathematical model that can be used to predict forces and deformations in every part of a structure from combinations of the pre-stressing action and various design loads. This is known as performing a structural analysis. With computers, it is a relatively straightforward step if a linear mathematical model is acceptable. However, if a nonlinear mathematical model is necessary, this step is much more difficult. Engineers must be aware that time-dependent or viscous deformation in pre-stressed materials can significantly decrease effective long-term pre-stress. Such losses need to be estimated and minimized. Given a set of functional requirements, there can be alternate structural forms that allow pre-stressing. Engineers must decide on which one to use. Engineers must define simple, effective, and safe pre-stressing processes for erection. This is often very challenging. Engineers must design stable pre-stress systems that have a known adequate stiffness and strength. And finally, in some cases, there is a prior challenging step that must be performed. It is finding the actual shape or form or geometry that can satisfy equilibrium and meet functional requirements. For the primary task of structural analysis of pre-stress systems, it is historical that John Butler Johnson, Charles Bryan, and Frederick Turnauer published an elegant, correct method for the great pre-stressed wheel built for the 1893 World Columbian Exposition in Chicago. Invoking only symmetry and superposition, they correctly determined that if the cable spokes were pre-stressed with a tension equal to twice the weight of one fully loaded gondola, then the spokes would always remain in tension even while directly above the hub. Their analysis may be the first time that the pre-stress required to preclude slackness in a system was determined analytically by U.S. engineers. Their analysis was linear in the sense that equilibrium was invoked in the original geometry of the wheel. But pre-stressed systems often cannot satisfy equilibrium in the original undeformed geometry. The most fundamental example of this is a tightrope. If a vertical weight or load is applied to a tightrope with pretension T, equilibrium can only be satisfied in a deformed or displaced geometry. A nonlinear structural analysis is required. Such an analysis yields several insights on structural behavior. For one, the initial vertical stiffness of the tightrope is proportional to the pretension, T. The tightrope frequency is proportional to the square root of the tension, and the stiffness increases as the weight increases. Linear or geometrically nonlinear analyses do not predict time-dependent pre-stress losses nor increases in deformations from viscosity of materials. Shown is a Douglas fir post that was pre-stressed by tensioning two exterior steel tendons. The viscosity of the wood caused a pre-stress loss of about 5.2% after about 1 month. For most materials, the rate of loss decreases over time and generally becomes negligible. The Douglas fir specimen was monitored for over 5 years, and no measurable pre-stress losses occurred after the first year. Often, there are alternate structural forms that meet functional requirements and that allow states of self-stress. Shown are two planar networks that allow states of self-stress. They may be distinguished by considering each joint as a point with a concurrent set of member axial forces. Each joint must satisfy two equilibrium equations. The number of unknown forces in a system on the left is less than the number of joint equilibrium equations. It is sometimes called a hypostatic system. The number of unknown forces in the system on the right is greater than the number of joint equilibrium equations. It is sometimes called a hyperstatic system. Both systems can be pre-stressed to have only tension forces in the cable members, but the stiffnesses of the two systems will be different, and they will carry imposed joint gravity loads very differently. Structural engineers must sometimes decide whether to use hypostatic or hyperstatic forms. Two large stadium domes exemplify alternate decisions. The engineer David Geiger chose to use a hypostatic form for his 1989 Tropicana field design, whereas Matthias Levy from Weidlinger Associates chose a hyperstatic form for his Georgia dome. Both domes had very large pre-stress forces in the millions of pounds in the members. Prestressing is often a dangerous process. 3 persons died during prestressing operations for David Geiger's dome for the Seoul, Korea Olympics. 1 person died and 2 were injured during prestressing operations for the Georgia dome. When prestressing, it is important to confirm the out-of-plane stability and stiffness of planar assemblies. Shown are 2 planar assemblies. The top drawing shows a system that is prestressed so that the diagonal members are in tension, indicated in blue, and the vertical member is in compression, indicated in red. The lower drawing shows a system that is prestressed so that the diagonal members are in compression and the vertical is in tension. Out-of-plane stability is a function of the position of the support of the vertical member. If stable, the out-of-plane stiffness is proportional to the pretension forces. 2 examples of planar pre-stress networks are Peter Rice's famous cable truss mullions for the Grand Serre at La Villette, France, built in 1981, and David Geiger's radial trusses for his Tropicana field. Both are stable and stiff out of plane and did not need lateral bracing. On the left, Peter Rice is demonstrating the out-of-plane stiffness by jumping on a mullion. The Howe and Pratt planar pre-stress truss forms behave differently. The pre-stress Pratt truss is unstable out of plane. That is, it cannot be built without lateral bracing, whereas the Howe truss is stable out of plane. Shown on the right is a small Howe-type pedestrian bridge post-tension to preclude compression in the top chord. The plane Howe trusses are stable and stiff out of plane. They do not require lateral bracing. It is often necessary to estimate the strength or capacity of pre-stress forms. The evident question is, does an initial self-equilibrated state of pre-stress decrease the maximum load that can be applied? That is, the load that causes a collapse mechanism in a structure. If the members and connections are ductile, an initial pre-stress state does not decrease the mechanism limit state capacity of a structure. This was shown by the Russian academician Alexei Gvozdev in 1938. This may be illustrated by considering a simple laterally loaded plane truss. The top left drawing shows a non-pre-stressed truss. Say that the truss capacity is controlled by the strength of the ductile diagonal. The maximum lateral load L that can be applied is the load at which the diagonal reaches its strength and the truss becomes a mechanism. The lower left drawing shows a pre-stressed Howe-type truss with contact-type diagonals that have a compressive strength but zero tensile strength. The load deflection behavior is shown for two levels of pre-stress F sub PS. The applied load increases the force in one diagonal and decreases the compressive pre-stress force in the other diagonal. The strength of the truss is the same as that of the non-pre-stressed truss for all pre-stress levels. But pre-stress systems can have much more complex geometries. This is an example of a pre-stressed three-dimensional truss called a tensegrity, designed and built by the artist Kenneth Snelson. It can probably safely be said that only the artist and his assistants understand how the geometry was achieved and how the pre-stressing was done. In general, tensegrities are characterized by individual compressive members connected only to tensile cable members. Engineers have endeavored to understand the geometry and structural behavior of tensegrity forms, which are generally hypostatic. The most basic tensegrity is a 6-member truss that consists of 3 compressive members and 6 tensile cable members. Engineers understand the geometry of this basic form in the following way. Say that the initial geometry is defined by the triangular prism shown on the upper left. The form is stiff and can satisfy equilibrium for an arbitrary load if rigid body motion is precluded by 6 appropriate restraints. The form cannot be pre-stressed in this original geometry. However, say that the original geometry is deformed as follows. Rotate the top triangle, allowing only the diagonals to change length. Hold all other member lengths fixed. At a rotation of 150 degrees, the diagonals will have minimum lengths, and the truss can have a self-equilibrated pre-stress state and in fact corresponds to the basic tensegrity form. The truss stiffness will be proportional to the pre-stress forces. The fact that systems that allow states of self-stress often correspond to geometries where one or more members have maximum or minimum lengths was first observed by the scientist James Clerk Maxwell in 1864. Consider next a quadrilateral prismatic truss. The truss cannot be pre-stressed in the geometry shown. The system is not stiff if a minimum set of 6 restraints are imposed to prevent rigid body motion. However, deform the geometry as follows. Rotate the top quadrilateral, allowing only the diagonals to change length. Hold all other member lengths fixed. At a rotation of 135 degrees, the diagonals will have minimum lengths and the truss can have a self-equilibrated pre-stress state. The truss stiffness will be proportional to the pre-stress forces. In general, consider an n-sided polygonal prism truss. It cannot be pre-stressed in the geometry shown. The system is not stiff if a minimum set of 6 restraints are imposed to prevent rigid body motion. But deform the geometry as follows. Rotate the top polygon, allowing only the diagonals to change length, holding all other member lengths fixed. At a rotation of 90 degrees times 1 plus 2 over the number of sides of the polygon, the diagonals will have minimum lengths and the truss can have a self-equilibrated pre-stress state. The truss stiffness will be proportional to the pre-stress forces. An example of this geometry is Kenneth Snelson's VX tensegrity at the Columbus Museum of Art in Columbus, Ohio. But understanding geometries that allow states of self-stress is only the first step for structural design of large pre-stress structures. Engineers must determine the pre-stress forces in all members, as well as member forces and stiffnesses under the design loads. And engineers must determine a process for erecting and pre-stressing a network. Form finding and structural design of innovative structural tensegrity forms are active research areas. A common methodology is to start with a network, which is generally hypostatic, and an initial geometry and member connectivity. Then computationally deform the initial geometry until a self-equilibrated pre-stress state exists, or until a quantity such as strain energy, member lengths, or surface area is minimized. The tensegrity concept has been generalized to include membranes in addition to compressive struts and cable members. As qualitatively shown in the images on the left, membranes generally form hyperbolic paraboloid surfaces at geometries that allow self-equilibrated stress states. In summary, pre-stressing has been used over much of human history and applied to most structural materials to assure functionality, enhance performance, and improve efficiency. Thank you.